This is Stefano Nasini, and this video is about projection. What is a projection? It is a linear transformation which allows to convert a vector B into another vector P, which lies on a line or on a linear space. The vector we obtain, P, must be as close as possible to B. And this requirement of closeness, of proximity, is guaranteed by the orthogonality between B minus P and A. That is, to get a vector P on the line through A, which is as close as possible to B, we must take a vector such that the difference with B is orthogonal to A. Okay, this will be shown. This property will be shown. The fact that this orthogonality guarantees the closeness will be shown in the final part of this lecture, of this video. Okay, let's take these conditions, these requirements, and let's see how to derive the projection matrix, how to derive P starting from these requirements on A and B. Okay, we have that the orthogonality, the proportionality of P is to A, no? P is equal to alpha A, and then we have the orthogonality of A and the error vector. When we say the error vector, we mean B minus P. Okay, this inner product, replacing P with alpha A in this inner product, what we get is that alpha must be equal to A transpose B over A transpose A. And replacing alpha inside this formula, we get that P must be equal to this quantity. Okay, now look at this carefully, because what we put into parentheses is a matrix. We have a column by a row, so a matrix. And here in the denominator, this guy down here is a scalar, a row times a column. This matrix here is what we call the projection matrix. Before moving on, let's ask some question about these guys, between questions about A and B. What happens if we double B? Okay, looking at the formula, if we double B, we obtain a projection which is double as well. But if we double A, nothing at all happens, because actually what we are using is not, what we are interested in is not the vector A, but the line through A. We are not projecting B onto a vector, but we are projecting B onto a line which are generated by A. A is a basis for this space. So intuitively, nothing at all happened to the projection when we double A, just because the space we are projecting on doesn't change at all. Some question about the projection matrices. What is the column space of the projection matrix? Well, just by reasoning about the meaning of the projection matrix, it is intuitive that the column space must be the line through A. Why? Because when we project a vector, we are let's see the picture. When we project a vector, the matrix P is giving us another vector which is on the line through A. So for whatever real vector of the same dimension, the matrix P is returning another vector which lies on this line. So the column space of this matrix must be the line through A. Okay, what is the rank of P? Okay, this is a rank 1 matrix, because this A times, this matrix is A times A transpose, and also this definition of P implies that P is symmetric. But the real property of P is that what really matter about P is that when we multiply P by itself, we obtain again P, and this is what we expect from a projection matrix, because when we project a vector which is on the column space of a matrix, we project it on the same column space, we should obtain again the same vector, no? By the definition we gave before. This fact that the square of the projection matrix is still the same projection matrix will be proved in the final part of this video. For the moment, just take the intuition. We project a vector into a plane, and then if we want to project again this vector we obtain, the result will be the same. So intuitively, a requirement of the projection matrix must be that its square must be itself. Let's move on to higher dimensional spaces. Suppose we want to project the vector B not on the line through a vector, but on a plane which is generated by the columns of a matrix capital A. Okay, once again we have that the projection must lie on the plane, so the projection must be a linear combination of the columns of A, and at the same time we have that the error vector, the difference between B and P, must be orthogonal to each vector in the plane. So formally we will have these two equations. We will have that P must be a linear combination of the basis of this plane. We say that this plane is generated by the columns of A, and then we have that the error vector must be orthogonal to each vector in the plane, and so particularly it must be orthogonal to the basis of this plane, and this is guaranteed. This property is guaranteed by requiring that the inner product between A and B minus P to be equal to 0. Okay, this condition lead to these conditions lead to these formulas. By replacing P in this inner product with the definition of P, which must lie on the plane, so we replace B with AX, we easily obtain that X must be A transpose A inverse times A transpose B. Then, replacing this in the formula of P, we obtain that P must be A transpose A inverse A transpose B. This guy here is a matrix, so the projection matrix will be A transpose A inverse A transpose. Okay, let's stop a second on to show some properties of this projection matrix. First of all, we might wonder whether we can apply to this inverse the property which says that we can inverse inside the parentheses this way. Why don't we replace A transpose A inverse with A inverse A transpose inverse A transpose? Okay, we get if it would be possible, what we obtain would be the identity matrix. So something is wrong here. What is wrong? Well, it is clear that A might not be square and full rank matrix, so we cannot compute an inverse of A. But suppose A to be a square and full rank matrix. Suppose A to be a square and full rank matrix. What we obtain if A is a square and full rank matrix? We obtain that A, the column space of A, will be Rn, will be the all Euclidean space of dimension n. So a vector B must be a vector B of the same dimension must be inside this space. So a projection would be B itself, and that's why we have the identity. So this is quite reasonable, and this is what I wrote here. Okay, now let's prove that the square of P is again P. So this is which is a requirement that we set in the beginning. Okay, let's multiply P by itself. Let's multiply A transpose A here, and we get A transpose A inverse times A transpose A. This guy is the identity, so that the result will be again A transpose A inverse A transpose. So again P. Okay, now what I want to talk about is a kind of application, or if you prefer, an extension to other problems of projection. Why we use projection? The main reason we use projection is because sometimes we have a system of equation of this form. Suppose we have this guy here, Ax equal b, and such a system might not be a solution, as sometimes happen. Suppose this system has no solution. Okay, we should stop, or we could either stop or finding a solution not to this system, but to an alternative system, which is defined as the previous one, except for the right-hand term, which is replaced with another right-hand term. So we might settle to solve ax equal p rather than ax equal b for a p which is as close as possible to b. But we know that this idea of closeness, of proximity, is exactly what is captured by the projection. We want to find the projection of b in the column space of A. We know that if the system ax equal b has no solution, it means that b is not in the column space of A. So let's find a projection of b in the column space of A. This will be our result. This idea is exactly what statisticians do when solving a problem of linear regression. Suppose we have a collection of points in the m-dimensional space, and we map those points in another space, in a one-dimensional space. In this case, if the mapping between this m-dimensional space and this line if this mapping is a linear one, if there exists a plane which passes through all the points, through the set of all points which interpolate to all points, well, this system will have a solution. So if the vector y is linearly explainable by x, by those variables, then this system must have a solution. Okay, but in real life things are not like that. There could be measurement errors or some kind of other randomness. So we probably have no solution in that system, and the method we follow will be to create some perturbation of the right-hand term, to introduce some error, and to try to minimize that error. Okay, the idea of projection we know that allow to find a linear combination of those explanatory variable x, which are as close as possible to the right-hand term y. Okay, let's call A this matrix here in order to be coherent with the previous notation. The idea will be to find this projection, and to find this projection, and this projection is found by finding the error term. By applying the previous equation, we get that beta will be equal to A transpose A inverse A transpose y. And this directly follows from the previous equations, and the error term will be that guy. But of course, we might obtain all this stuff, we might derive all this stuff by calculus, because we said that the projection guarantees the closeness to the original right-hand term. We know that projection and the orthogonality between the error term and the column space guarantees closeness and proximity, the highest closeness and proximity to the original right hand term. Okay, but we must prove this. We should be able to show that this is the case. So let's define what we mean for error. Okay, we define error as square error. So the difference between the original right hand term and the one we obtain after projecting. We show that this this error and the projection we obtain is exactly the one derived in the beginning of this video. So let's minimize with respect to beta y minus a beta transpose y minus a beta. Okay, this guy is equal to that. Applying the first order conditions, derive with respect to beta equal to 0, and we obtain this equation, and beta will be equal to a transpose a inverse a transpose y, and the error term will be this one. Okay, you can check that this is exactly the same. So what we proved? We proved that the projection is exactly the vector which minimizes the square error, and we proved that the square error is indeed the one we obtain by projecting.